Hi everybody, I hope you all are doing great. So today also, as you can see, time is 2 a.m. and here we are learning DP, right? So I hope you all are enjoying the content and I have seen support from your side. Like although it is a very initial channel which I'm having, but of course seeing this kind of supports really motivates me to, you know, just be consistent at my work, right? So let us get started with the next problem, which is gold mine problem. So let us read the problem statement. Given a gold mine called M. Okay, apparently they are calling a gold mine M. So of n cross m dimensions, all right. Each field in this gold mine contains a positive integer, which is the amount of gold in tons. Of course, initially the miner can start from any row in the first column from a given cell. A miner can move to the right to the cell diagonally upwards towards the right to the right cell and to the cell which is diagonally downwards towards the right. Okay, find out the maximum amount of golds he can collect. So this kind of gold mine they are giving me, and you can see the output is 12. Let us analyze this on the board and then we'll be in a better position to try to contemplate the solution itself. So this is the exact same test case given in the problem itself. Let us try to analyze what they are saying. What they have given in the problem is that initially the miner can start from any row in the first column. So according to them, this is the first column and the miner can start mining from any column, right? Any row in this particular column. Let us say the miner starts from this particular column, right? So he will connect two gold, right? Now from this step, he can either go diagonally upwards towards right, diagonally like downwards towards right and right. So these are the three steps he can take from any position. If the miner is standing here, he can either go up, which is of course an invalid index, where he'll not be able to go. He can go right or he can go diagonally down. If he's standing here, he'll be able to go this and these positions, right? So let's start from 2. Let's say he collects this much gold and then he goes up. He collects 3 amount of gold and then he goes down. He collects this amount of gold. And therefore you can see that how much gold he's collecting in this kind of path. He's able to collect, a 5 plus 4, which is 9 gold in this kind of path, right? Pretty similar to minimum path sum problem which we saw yesterday, right? In this problem, the main focus will be on the tabulation part of the code because we have not seen a iteration on tabulation so far. So I just wanted to show you some iteration on tabulation code as well, right? So of course here, if I get the best output, so of course let's say he from all these rows, any row he can start. Let's say he starts on the first row, then he goes diagonally down to the right and then he goes diagonally up to the right, or say maybe right itself, right? The output will be what? The output will be 12. 6 plus 4 plus 2, which is 12, which is the best gold he can get in this kind of test case, right? They can have a bigger like 2D array as well, and for that you can of course imagine there'll be multiple possible solutions, right? And of course the best solution will be one only, but to achieve that it is possible there can be multiple paths, right? So this is the problem statement itself. You have to find out the best path the gold miner can take and the profit associated to that path, right? You just have to find the profit associated to that path. So let us see this problem, that how we are going to solve it recursively. I'll not focus more on recursion in this video because minimum path sum we have covered recursion in great depth in the last problem itself. In this particular problem, my main focus will be on understanding the tabulation part. So let us quickly see the recursive. So if we start the recursion part itself, of course we can see that I can start from any of the cells given in the first column, right? I can start from any row on the first column. Let's say I first try to get the best path I can get. If I start from 0 comma 0, so from 0 comma 0 definitely recursive call is there, so three choices we are having. So from here there will be three choices. If I go diagonally up, right, or diagonally down, if I go diagonally up here, if I go in this index, so when we go up, I talked about this in the last video. So when we go up, it is I minus 1j. When we go right, it is I j plus 1. When we go down, it is I plus 1j. When we go left, it is I j minus 1, right? So when I go up from a particular cell, it is just I minus 1j. So that will be, and diagonally up will be, diagonally up, here we are having diagonal steps as well. So I minus 1, j plus 1. What is diagonally down? It is I plus 1 and j plus 1, right? So I minus 1, j plus 1. So minus 1 comma 1. This is an invalid index, so I'll simply return that he'll be able to make 0 gold out of this path. I have to return the maximum gold. I'll take the minimum possible gold, which is 0. I'll return that. So R, if I go right from this particular space, you can see I'll reach 3. If I reach 3, right, if I'll reach 3, so I'll be able to make like how much. So if I'm going route right, so I plus j, I comma j plus 1, I comma j plus 1, 1 comma I comma I will be as it is j plus 1, right. If I go diagonally down, I plus 1 comma j plus 1, so 1 comma 1. Both of these are valid indexes. Let us explore their possibilities. So from this particular index, I 0 comma 1. If I go diagonally up, if I go right, if I go diagonally down. These are the three options I'm having. If I go diagonally up from this particular position, you can definitely see if I'm going diagonally up from this particular position, I'll simply reach where? I'll simply reach a cell where I minus 1 comma j plus 1, I minus 1 comma j plus 1. This is definitely an invalid index, so I will return 0 from here as well. I'm directly handling those conditions where we are returning 0. If I'm trying to go right towards the right side, I'll reach where? I'll reach I comma j plus 1, which is 0 comma 2. If I go diagonally down, you can see I'll be reaching 1 comma 2. I'll be reaching 1 comma 2. Right. So these are the things I'm having. If I go, these are all the possibilities I'm having. So basically in recursion, we are trying to find out all the possible outcomes which I can get. And I think this is a very easier way to understand dynamic programming problems, because if you are able to get the recursive code now, the logic is there. The only thing remaining is to optimize that using memoization and then further convert memoization to tabulation itself. So let us see this example of 0 comma 2 itself. 0 comma 2, I am having three options from here, and 0 comma 2 you can definitely see all these options will be out of bound itself, right, because we are on the last column itself. So you can definitely imagine that from here I'll be receiving 0 from every choice, because all of them will be, all their indexes will be out of bound itself, right. So the best I can do from my options plus my data plus the gold I can collect from this particular index, that will be what? 0 comma 2. What is gold? What is the gold on 0 comma 2? It is 3, plus the best I can do is 0. So I can do best as 3 only, right? If I am standing on 0 comma 2, I'll be able to do the best, which is on third, like 3 amount of gold, right? If you look at this 1 comma 2 index, of course 1 comma 2 is also on the last row itself, so all its own possibilities will also be from, like they will be out of bounds only, so I'll be returning 0 from them only, right? And as you can see that I'm getting best as 0 from all these here. From here I make three choices, I'll be having no better choice, all of them will be out of bounds, so all of them will be resulting to 0, and hence my data, which is 4, plus the best I can do, which is 0 from all these choices, maximum is 0 only, right? So 4 plus 0 is 0, so from this index I'm able to make 4 the best, right? Now 0 comma 1 has a choice. Here you have to understand very closely. 0 comma 1 is having a choice. If 0 comma 1 is having a choice, you can see is it can go either right or it can go either down. If it goes right, it is getting the gold 3 tons of gold, right? If it is going diagonally down, it is able to get 4 tons of gold. Which is better? Definitely 4 tons of gold. I'll be going with diagonally down plus the gold I can collect on my index, which is 3. So 4 plus 3 will result 7. So I'll return 7 itself from here. Now 0, if it goes right, it is getting that I'll be able to make 7 the best. If it goes diagonally down on 1 comma 1 index, right? I think we have not calculated for the answer, right? Yes, we have not calculated for this. So let's see for 1 comma 1. 1 comma 1 also will be having three choices, and you can of course imagine these three choices are the last row only. So one will be diagonally upward, right? This is diagonally upward choice. If I go diagonally upward, I'll be standing on I minus 1 comma j. Definitely if I, from this index, if I go here, I'll be on 0 comma 2, right? 0 comma 2, I minus 1 comma j, then I j plus 1, I j plus 1, then I plus 1 j plus 1, 2 comma 2, of course, right? So these are all the things, and from here you can definitely imagine that all these are on the last column itself. All their choices will result out of bounds only, and since they're resulting out of bounds, they will result to 0 only, right? So the best I'll be able to do from this 0 comma 2 index will be this 3 only. I'll be returning 3 here. The best I can do from 1 comma 2 will be 4 only, so I'll be returning 4 from here. The best I can do from this particular index is 4 only, I'll be returning 4 from here. And you can definitely see the best choice is 4. Any of these 4s is the best choice, plus the data on 1 comma 1, which is 1. 1 comma 1 will be returning 5. Now tell me, what is better option for 0? When 0 goes to the right, it is getting 7. From here, you can say we can take this path, and when 0, like we are going to diagonally downwards from this particular index 0, 0. You can see the best I can make is this or this, which is the 5 only, right? Best is of course 7, so I'll take 7 and plus the data I can get, it is 7 itself. So 7 plus 1, which is 8 itself, right? So if the gold miner starts its journey from 0, 0, he'll be able to make 8 profit out of it. Now this is just the beginning of the question, because we have only tried 0, 0. We have to do the same thing for 1, 0 and then from 2, 0. Same recursion trees will be given, and you can definitely see, although we'll be making different recursion calls for every row, right? Because miner can start anywhere. I don't know what's the best position to start. I have to calculate that, right? So since miner can start anywhere, you can definitely imagine now this particular index will be having the best answer from these three choices only. Now every time, even if the miner is starting from here, answer for this would be the same. Now this means that all the calls we'll be doing for every row, the memoization array will be the same. Okay? This is the recursion solution of this problem. Let us code this out quickly and then move to memoization and then move to tabulation. So let us look at the recursive code for this itself. So of course, static int, right, recur. I'll be having this ARR. I'm calling this grid as array. I'm not calling it n, I'm calling it ARR. I'll pass I, I'll pass j. I and j are the indexes which I'm standing on. And this is pretty much what the data require, right? So these are the things. So integer n I'll extract is equal to ARR.length. Let me just zoom in a little bit. So ARR.length, integer n is the ARR of 0.length, correct? Now if I becomes smaller than 0, right? Or what else can be the case? If j becomes can j be smaller than 0? No, because we are never doing j minus 1. The only operations we are concerned with are I minus 1, j plus 1, like this I minus 1, j plus 1, I j plus 1, and I plus 1, j plus 1. So you can definitely see we are not concerned with I, like j minus 1. So j cannot go less than 0, right? Because we are always increasing j. So j, like j less than n, if j is greater than or equal to m, or if j is I is greater than or equal to n, right? Because I can go out of bounds from down. I plus 1 we are doing, I minus 1 also we are doing, and we have to handle both the cases for I. So if I is becomes less than 0, or if j becomes greater than or equal to m, or if I becomes greater than or equal to n, this is out of bounds condition, so I'll return 0, right? Now what are the other conditions other than out of bounds? I'm having three choices: integer, right, diagonally, diagonal up, diagonal up is equal to recur for ARR I minus 1 comma j plus 1, right? That was diagonally up, I minus 1 comma j plus 1, right? Diagonally down, what was diagonally down? Right? What was diagonally down? Down, it was I plus 1 and j plus 1. And what was the other thing which is only right, going only right, is ij plus 1, right? Simply that is ij plus 1. So these are the three cases I'm having. I have to return what? Return math.max of the maximum of all these cases. So math.max of right, comma, math.max of diagonally up, comma, diagonally down, right? So these are the cases I'm having, plus what? ARR of I comma j. So these are all the cases I'm having here, and this is the recursive solution for this. The only thing which is remaining is I have to call this recursion function from all the rows of the first column. From all the rows of the first column, I have to call this function. So I'll start by, I'll take an integer maxi is equal to 0 initially. I'll store the maximum gold. I can correct maximum starting point goal in this particular variable. I'll start from, I'll iterate on all the rows, right? So what I'll do, I'll call integer gold I can get if I start on this row is equal to recur for, will be recurring for array. I'll pass as it is ith row I'll pass and column number will be 0 every time, right? So for all the columns I'm trying, I'll simply do what? I'll take the maximum of these variable. Max is equal to math.max of with maxi itself. In the end, I'll be returning maxi itself. And that would be the answer for the, you can say, this sample test cases would run just fine, this kind of code, right? Let us see if they are working fine or not. So you can definitely see 12 is the output and sample test cases are running just fine. So now is the time to convert this recursive code to memoized code. So for memoization, I need a space, right? And what will that space look like? Definitely you can see in the recursion call, I and j are the two parameters which change. So definitely we'll simply say that we will require a 2D DP for this kind of thing. So 2D DP is equal to new integer. N comma n will be the dimensions for this DP because I and j are not exceeding n comma n. For that we handled the out of bounds case, right? So DP is done. And to convert this recursion code to memoization code, let me write this as a different function. I'll just write it as a difference function here. Wherever recur is written, I'll simply write memo, right? I'll rename this function basically. After we rename this function, what will happen? I've renamed this function. Now I'll pass a DP array here as well, right? Integer array DP. DP array I'll pass here, and all these recursion calls will also have this DP 2D array. Alright. Now the thing which is remaining is simply I have to remember the solution, recall the solution, right? So if DP of if I and j are in the range, and if DP of I comma j is not equal to 0, this means that that place is filled because they have already given us every time they'll be having a positive value. Actually, they are having zeros as well. Okay, so they have not mentioned it correctly here then because they are giving us always the positive values. So we don't have to worry. I'll just fill this DP all the internal 1D arrays with -1. I'll just fill this 2D DP with -1 and then -1 will act as a parameter. So if DP of ij is not equal to -1, this means that we have filled somewhere there. And if we have filled somewhere there, I'll simply return DP of I comma j. Correct. And before returning, we will remember the solution for future reference. So I comma j is equal to this, right? So this will ensure that you are using the DP array in Memoisation Code. The only thing which is remaining is I'll simply fill all the internal arrays with then an I plus plus. So I'll just simply do arrays dot fill. I'll fill DP of ith array with -1. All the internal 1D arrays of this 2D array will be filled with -1s, which will denote that we have not touched that particular index, right? So this is the memoized code. Let us quickly, instead of calling the recur function, let us call memo function and it's called memo function and pass DP here, right? And then let us try to run this code. Let's see if we have made any error or not. So, okay, it's looking fine. Let's try to submit it and let's see if it gets accepted. So it is passing successfully. Let us quickly look at this tabulation because that is the main thing of this video, right? Let's look at the tabulation part of dynamic. So although you can definitely apply the trick we have learned to convert memoization to tabulation and the code will just run fine. But I want to show for your knowledge itself, just the tabulation approach. How can we derive the tabulation approach of this problem? Because in this particular problem, it is actually possible to directly derive tabulation as well, right? So now you can see in tabulation, in recursion, I'm starting from this particular row. In tabulation, from where do we start? We start from the base case. Base case is, can I say this is the last column? Is the base is acting actually like a base case? Because from this column, if I'm already standing in the last column, I'm not making any more recursive calls from there, right? So since I'm not making any recursive call, I can also treat this as a base case, right? So I'll start filling this column first and let us try to do that. So can I simply say for this last column, I can directly fill all this data here because that is the base case. I will directly fill this data here, correct? For this last column. In tabulation, now when you're trying to derive tabulation directly, that is also possible in some problems. You try to fill whatever you already know in the DP itself, right? And DP of course will be 2D because in recursion we are taking two parameters. So definitely here also DP will be 2D only. So I have filled this correctly for all the base cases. Let's try to fill these people now. I'll be filling in this order only because I have to, this is bottom up. We are going from the base case all the way to the thing I want to solve. So I want to fill this particular cell. This particular cell will choose the max of all these things. You can see this will come out to be 0, this is 3, this is 4. 4 is maximum. What do I want to keep? maximum of all these values plus the value which is here. I'll keep 4 plus 3 which is 7. Correct. Here what do I want to keep? The maximum of all these things which is 4 plus 1 which is 4 plus 1 which is 5. Here what do I want to keep? Maximum of all these things which are after me plus 6 which is 10. Here what do I want to keep? Maximum of all these things plus what? 7 is definitely the maximum plus 1 which is 8. Right. Maximum of all these things which is 10 plus 2 which is 12. Maximum of all these things which is 10 definitely plus 0 which is 10 itself. And from the first row, can you simply derive that 12 is the best you can make? So we'll be doing similar thing only in tabulation itself. We'll be starting a loop from where? We'll be starting for int j, because column we are changing one by one. J loop will be outside I loop, right? J is equal to m minus 1 initially because we are standing on last column, m minus 1. I'm directly writing the pseudo code as well. So for j, let me write it in a good handwriting for a moment. So for int j is equal to m minus 1, j greater than equal to 0, j minus minus. Correct. And what am I supposed to do here? I'll be traveling all the rows. So from the 0th row to the last row, for int I is equal to 0, I less than n, I plus plus. Okay, I have traversed. Now what do I have to do? I have to make 3 choices, right? On dp of I comma j, what do I want to keep? What do I want to keep? I want to keep the max of 3 choices plus ARR of I comma j. The data on that particular index is I want to keep, right? And of course, if I and j is a base case, if we are on the last column, this is the base case. I don't have to do all this stuff. I'll just keep whatever data is on ARR of I comma j. So let us quickly code this pseudocode type thing out. I think the tabulation code is pretty much clear to everybody. Let's try to quickly code it and then wind the video itself. So for the tabulation code itself, I'll create a static int tabulation, and in this tabulation, I'll pass array, I'll pass integer 2D array DP, right? Whatever we are making DP, I need a 2D array DP for this as well. So I'll make this thing. Now, we'll be starting filling the tabulation code from where? For integer, where for integer I is equal to, for integer j is equal to m minus 1, I'll simply write n comma m as well. So I'll write m minus 1, j greater than equal to 0, j minus minus. Now from where do I want to write start I? I will be traversing from 0 to row to last row for integer I is equal to 0, I less than n, I plus plus. Now if this is the base case, first I have to write the base case. If what? J is equal to m minus 1. If you are on the last column, then what do I want to do? Simply dp of I comma j will be error of I comma j, right? Because if we are on the last column, I simply fill whatever data is on the last column, right? I simply fill this data, right? Now this is the base case which is 100, right? And else if I'm not on the last column, what am I supposed to do? I'll get this data, right? Diagonal up, right, and diagonal down. So integer diagonal up is equal to dp of, I'm trying to access what? I'm trying to access dp of diagonal up is what? Which index? It is I minus 1 comma j plus 1, I minus 1 comma j plus 1. Int, right is what? dp of I comma j plus 1. Int down, diagonal down is what? dp of I plus 1 comma j plus 1. Now we have calculated the diagonals, we have done the work, and we are ready to go. Now the only thing is remaining is I have to take what? dp of I comma j will be simply this exact same line, right? The what? The max of diagonal up, diagonal down, and dp itself, error of like right itself, right? Let me make it a little bit smaller so that it's visible to everybody. So yeah, this is the line of code we are interested in. I hope this is visible to everybody, right? So this is the line of code which is which I'm storing when I'm not on the last column. In the end, I'll simply return what? I'll traverse the first column. I'll take an integer maxi is equal to 0. I'll traverse the first column for integer I is equal to 0, I less than n, I plus plus, all the rows of the first column. and maxi is equal to math.max of maxi comma dp of ith row and 0th column. I'll simply return maxi from here, and this will be the tabulation code for this problem. Let me, call this function itself. Instead of returning maxi, I'll simply return tabulation of array I'll pass and dp I'll pass, right? And one thing but is remaining, we are not handling cases for out of bounds. These conditions are not handled, right? Here, can I simply write the ternary operators and can be handled like that, right? Let me write ternary operators here and then we will handle these conditions. So you can see we are on this particular line of code, I'm trying to do I minus 1. If I'm trying to do I minus 1, can I simply say that I minus 1, if it is greater than equal to 0 and if j plus 1 is what? Less than m, then only try to access that particular index in the DP, or else you will try to term it as 0. This particular line, only j can go out of bounds because only j plus 1 is getting done. So if j plus 1 comes less than n, if j plus 1 comes less than n, then only try to access DP array, else 0. Diagonal down is what? I can go greater than equal to n and j can go greater than equal to m, right? If I plus 1 is less than n and j plus 1 is what? Less than m. J plus 1 is always less than m, right? Because j is only going plus 1 every time. Then only try to access this DP array, else consider it as 0, right? So this is the tabulation code itself. Let us quickly compile and run it and see if it is working, if we have made any syntax mistakes or not. It is working just fine. Let's try to submit this. And the solution is working perfectly. And these are all the codes for recursion, memoization, and tabulation for this very famous goldmine problem, right? Company tags, you can definitely see it is a very famous problem. So like asked in famous companies. So now if you're wondering what time is now, you can definitely see here. So yeah, so this is it for this video. Thanks a lot. If you're enjoying the content, please support the channel, right? I am already like very amazed by looking at your support. So thanks a lot for joining me with me on this video. See you all in the next video. We'll be solving DP problems daily. Consistency is the key, remember, right? So see you all in the next video. Thanks a lot for joining. Until the next video, guys. Bye.